Every single smartphone, computer, and car infotainment screen ultimately owes its intelligence to something almost invisible, but absolutely vital, and it all starts with grains of sand. Behind every swipe, click, or stream, there's a story that rarely gets told. How do we transform ordinary sand, one of the most common substances on Earth, into the intricate microchips powering our digital world? It's a process that seems almost alchemical, taking something basic and turning it into the engine of modern civilization. But the magic doesn't begin with just any sand. It begins with a very specific kind, silica sand, or quartz, which is composed almost entirely of silicon dioxide. Pure white beaches, those are often made of quartz, but even here, impurities abound. Microchips demand an astonishing level of purity, so much that even a hint of iron or a trace of other elements can ruin the entire process. So why silicon? Why not gold or some other metal? Silicon sits right in the middle of the periodic table's fourth row. It's special because it's a semiconductor. It can conduct electricity under some conditions and act as an insulator under others. That flexible behavior is perfect for building switches, the basic on and off language of modern electronics. But the sand itself is just the raw ingredient. To unlock the power of silicon, we first have to separate it from its stubborn partner, oxygen. That means ripping apart one of the strongest chemical bonds in nature. Industrial furnaces do the heavy lifting here, heating a mixture of quartz sand and carbon to temperatures above 2,000 degrees Celsius, hotter than molten lava. The carbon rips away the oxygen molecules, releasing them as carbon dioxide gas. What's left behind? Shimmering, molten silicon, which solidifies into dull gray lumps. Now, this silicon is about 98 to 99% pure. Good, but nowhere near the level required for building microscopic transistors measured in billionths of a meter. The next step is purification, turning crude silicon into something called electronic-grade silicon. This is where things get mind-bending. Factories vaporize the crude silicon and then pass it through a complex series of chemical reactions. Imagine an enormous game of molecular musical chairs. Impurities are shuffled away, and only the purest silicon atoms remain. The result is a solid rod of silicon so pure that a single atom of impurity among a billion silicon atoms would be unacceptable. This purity is monitored constantly using lasers, X-rays, and other high-tech tools. The rods are crystal clear, glimmering with an almost alien beauty. Now, the silicon must be shaped into something useful. Thin wafers that will become the foundation for microchips. The rods are slowly lowered into a vat of molten silicon and carefully rotated. It's a dance between heat, gravity, and precision engineering. As the rod is pulled out, a near-perfect crystal structure forms, spiraling upward in a slow, controlled motion. This technique is called the Czochralski process, a name that sounds almost as intricate as the process itself. The resulting single crystal cylinder is called a Boules. These Boules can weigh hundreds of kilograms, stretching up to a meter long, almost like giant metallic carrots. Now, imagine slicing that boule as finely as possible, producing mirror-like silicon discs just a fraction of a millimeter thick. These are the wafers, smooth, flawless, and ready for the most complex technology humans have ever built. But a wafer is just the canvas. The real artistry happens when engineers etch unimaginably tiny circuits into its surface. Think of it as building a city, a bustling metropolis, at a scale where streets are only a few nanometers wide. Even a single speck of dust would be a boulder. This is where photolithography comes in. It's a word borrowed from photography, using light to sculpt shapes. Engineers coat the wafer in a special light-sensitive material, project intricate patterns onto it using ultraviolet light, and then wash away the exposed areas. Layer after layer, patterns are built up, wiring together millions or even billions of transistors on each chip. To put it in perspective, the most advanced microchips today contain more transistors than the number of people on Earth, and they all fit on something smaller than a postage stamp. Each step demands absolute cleanliness. Factories use air filters hundreds of times better than those in hospitals. Workers suit up head to toe to avoid shedding a single skin cell, because even the tiniest contaminant can destroy an entire batch of wafers worth millions of dollars. Once the circuits are complete, the wafer undergoes a series of chemical and physical refinements. Microscopic wires are laid down, components are interconnected, and layers are stacked almost like the floors of an ultra-miniature skyscraper. Finally, the wafer is diced into individual chips, each ready to become the brain inside your laptop, your car, or your phone. All this from the ordinary grains of sand. There's something poetic, almost philosophical, in the fact that our modern digital reality is built on the same material that forms ancient beaches, glass windows, and hourglasses. What started as sand on a shoreline ends up as the silent conductor of binary code, mediating our emails, our conversations, our creativity. Pause and consider how many everyday miracles depend on this unbroken chain of precision, ingenuity, and patience. From the first shovelful of sand to the glowing chip in the heart of your device, it's easy to overlook just how much of our world relies on this process. If the factories stopped purifying silicon today, progress in computing would stall. Phones would freeze at their current capabilities. Even advances in medicine, space exploration, and climate science would slow to a crawl. Think for a moment about the journey of a single atom of silicon. It might have spent millions of years buried beneath a desert, tumbled to the surface by wind and rain, then smelted in a superheated furnace, purified almost to perfection, and shaped by human hands into something extraordinary. Without that journey, the memory chip in your camera or the processor in your favorite game console simply wouldn't exist. The story of sand turning into microchips isn't just about chemistry or engineering. It's a story about vision, about seeing potential where others might see just dust or debris. Each step in the process reflects a fundamental principle of invention. Sometimes the most world-changing advances come from the least likely of places. Now, think about the world around you for a moment. The next time you hold a phone, swipe a screen, or send a message across the globe, remember the mind-boggling passage from sand grain to silicon chip. Remember that in our digital age, even the most ordinary things, when shaped by human creativity, can become extraordinary. So, what does it take to transform sand into the heart of every digital device? The answer is a grand convergence of science, engineering, and imagination, and a deep respect for the materials that connect us all across time and technology. In the end, the journey from beach to microchip is a reminder. No material, no matter how humble, is without potential. In the hands of curious and persistent people, even grains of sand can help us build entire worlds, real and virtual alike.